The world is becoming more nano, and at the same time, time scales are compressing as well. Speed is important, time is money. And silicon photonics is a manifestation of this. There's more and more data being pushed around between more and more data centers, consuming more and more energy. And silicon photonics is an answer to these things. It offers new parallelism, new data throughput capability, the ability to make distributed data centers, the ability to scale with the world's appetite for data, which is exponentiating every day. To make silicon photonic devices, though, requires tests. You have to test these devices before you package them, because the preponderance of the cost in manufacturing these devices is actually in the packaging process. The costliest thing that a silicon photonics manufacturer can do is package bad product. And so it's necessary to test these devices as soon as they are manufactured on the wafer. That's what this is all about. This is a system that we call the Fast Multi-Channel Photonics Alignment System. It's made for testing devices at the wafer level and also further on in the production process as well, and also for packaging. What is unique about this system, which is a finalist for the PRISM Award, is its capability of performing simultaneous global optimization across all of the inputs and outputs that a silicon photonics device might have, including all the degrees of freedom that might impact each of the couplings. So you can have a device with n inputs and m outputs, each having q degrees of freedom, and all of those quantities can be optimized globally in one step with this system, because it has some radically different new technology that allows all these alignments to be performed simultaneously, even if they interact, which is often the case with the short waveguide devices that silicon photonics devices frequently contain. As you can see here in this particular demonstration, we're cycling. We've fashioned a silicon photonics device using a carbon fiber wafer in this case, because regular silicon photonics wafers are worth millions of dollars. So this way we've fashioned a waveguide into this carbon fiber disc, and you can see we are probing it. And we're able to align both the input and the output of this waveguide in typically much less than 1 second. On the screen of the computer behind it, you can see some fast profiling that's built into the controller of this system, and also the fast multi-channel simultaneous parallel gradient search that optimizes the global couplings of the device all at once, in one step. This helps our customers achieve their process economics goals. I mentioned earlier that there's both a compression of physical scale, meaning things are becoming more and more nano as time goes on, but also speed is very important. That's why we've come up with a broad line of direct drive, voice coil, and linear motor driven stages that offer extreme accelerations and extreme bandwidth for making dynamic motions and things of that sort. In parallel, we have also developed some technology that's useful for measuring very, very fine forces. For example, in the photonics industry, it can be used to detect the contact of an optical fiber with a device, a waveguide, or something of that sort. Very, very fine force sensing capability combined with sub-micron positioning resolution capability. This particular device right here, you can see, is making contact with an object, in this case a small metal battery case, and performing calibrated force motions. This is a mechanism which has proven very useful for the calibration, validation, and production test of touch-sensitive devices. And that's important because when you look at the history of computers, personal computing, every major revolution has been driven by a new kind of user interface. The graphical user interface, the mouse-driven user interface, and now the touch-driven user interface. So it's important when you're manufacturing these devices to validate their performance in a high-volume situation. So this mechanism can do that at high speeds, high throughputs, and good production economics. One of our recent investments has been in air-bearing manufacturing capabilities and technologies for making ever faster, ever smoother, nanoscale capable positioning equipment with very long travels. Air bearings are not by any means a new technology, but we have some very talented engineers and very clever designers who have helped take air bearing technology to the next level. You can see here, this long travel XY stage incorporates some very novel controls that eliminate the vibration caused by the motion of the system. You'll notice that that pendular mass that's sitting on a springy rod on top of the stage is no longer oscillating. That's because we have started and now we have turned off the anti-shaking capability. So you can see how dramatic the impact of that is. Again, this goes to the compressing speed tolerances the customers have. They need things to be faster and faster and faster. They can't afford to wait for settling times, for things to calm down after a motion. So being able to eliminate those unwanted vibrational responses is a very key capability for improving process economics. The world is getting smaller, and so are motion devices. These are mechanisms capable of many millimeters of motion, but you can see they're smaller than the matchbook. This one in particular is a 6 degree of freedom positioner using this new Q-motion technology, is what we call it. It's a piezoelectric driven technology that's capable of essentially unlimited travels. So we have built this into it's a hexapod-like configuration we call a space fab. This one's very, very small. It can be made in vacuum compatible configurations, and it can be run either open loop or closed loop. In closed loop form, we can achieve up to 1 nanometer resolution because the world is getting smaller. In fields such as atomic force microscopy, single molecule biophysics, semiconductor microlithography, what these all have in common are the necessity of controlling motion down to the sub-nanometer level. To do that requires piezoelectric technology. There is currently no alternative. And in fact, the ultimate resolution for which piezoelectric positioning technology is capable is not yet known. That's why piezoelectric positioners are used for things such as atomic force microscopy, where motions down to the sub-subatomic level are required.